All right, hello everyone. It's kind of strange introducing yourself, but not in person, but on a video screen. So I haven't done that yet, but that went quite well so far. So hopefully everything goes well from now on as well. So I'm going to show you how you can build a real-time streaming analytics platform with open source components. And as I've already introduced myself by video, I only want to do that rather brief with that slide. So I'm kind of a search guy. I work a lot with search technologies. I like solving problems with search. And the two main open source search technologies are Solr and Elasticsearch. Today will be a little more Elasticsearch related, but I'm also a Solr trainer and I've written a book about Solr, which is in German, so that's probably the first reason why most of you will not buy it. And the second one is it's really old, so please do not buy my book, although I get a small amount of money for each purchase. But the online documentation of Solr is far better than my book, now at least, but it was really good the time when we wrote it. So what will my talk be about? I'll dive in with just a brief overview of what unstructured data is, because we'll deal with unstructured data during that talk. I'm going to dive into the requirements of a real-time streaming analytics platform, so what you need to deal with when you want to set up one yourself. I'm going to show you a brief overview of how you can combine several components to have something like a reference architecture. And then I'll show you which open source components you can use and what their value is to you. I will show you a brief demo which is comprised of some of these open source components. Hopefully everything goes well. So it went well yesterday. I tested it, and just 10 minutes before the talk I tested it, and hopefully everything runs. Afterwards we'll do a small recap to see how what I've shown you matches the requirements of a real-time streaming analytics platform and how future improvements of the small demo I put together might look like. So unstructured data, I think everyone knows that data is being generated at any time in any company by any person. There are huge amounts of unstructured data, so everything that is text-based, like emails, reviews, documentations, presentations, that is all text-based, and that is unstructured data, and that data is usually spread across many silos, which means that everyone has limited access to that data. And limited access means also limited readability and accessibility. So you need to kind of find a way to stream that data into a platform, so there can be, like actionable insights where you know what to do with that data from what's in the data. When we look at the requirements of such a platform, there are a few key aspects. One is performance, because you kind of want, low latency, which means that when an event is generated, you want to action on that rather quickly and not 2 days after the event was generated. You might also want high throughput, so not only one event per second or 100 events per second, but maybe 10,000 of events per second. So that's a key aspect. Manageability is another one, so everything needs to be rather easily deployed. And you also need APIs and KPIs for monitoring everything, that everything goes right, not wrong. Because if things go wrong, you need resiliency. And resiliency means that even if a part of your platform goes down, you don't want the whole platform to go down. Scalability is another key requirement, because, usually you start small with a small amount of data, with maybe 100 events per second or something like that. And then you want to grow tall, so more use cases, maybe more data, more insights. So scalability is another requirement of such platforms. When it comes to not only what you need now, but maybe in the future, data protection and multi-tenancy is another requirement. So you kind of need an end-to-end governance process to know who belongs which data, who has access to which data. And you might have multiple consumers of data, and you need to make sure that each consumer only has access to the right pieces of data in your system. You also need to be compatible and extendable. Compatible means you kind of need to make sure that when you scale across multiple data centers, everything still goes well. And scaling across multiple data centers might not be a key requirement for any use case, but especially in the financial sector, for example, you need to scale across multiple data centers to make sure if one data center goes down, your platform is still up and running. Expanding your platform means, well, you might want new use cases, or you want to extend existing ones. And that might not be a key requirement from the beginning, but if you don't, well, take that into consideration, then you might end up, well, breaking stuff when it comes to future requirements. So that is something you need to take care of as well. So how might a platform like that looks like? We now have an example here. We have reviews, and I have real Amazon reviews with me, and we pretend that they are generated in real time. And when they are generated, we kind of need to fetch these reviews, and we fetch them with a tool called Beats, which is a tool from the Elasticsearch, and the Beats component here fetches all our reviews and pushes them to a Kafka topic, which is within our data layer, something like the data integration part of it. From our Kafka reviews topic, a Spark streaming context reads everything, so every review that is generated, and, well, throws it against a machine learning model to see whether this review is a good one or rather a bad one based on the text of the review, not on the, well, amount of stars that it got by the reviewer itself. The machine learning part then, well, it has an output, so it's either good or bad, and the review with the output is again written to Kafka, another topic, analyzed review topic. And from Kafka then it's read by Logstash, which is another component of the Elasticsearch, and then writes everything to Elasticsearch in my demo. Usually you would probably also want to write it to a, let's say, archive storage or something like that. So Hadoop distributed file system is one example here, but any data warehousing component would be capable of that. The streaming and machine learning in this demo is done by Zeppelin. So Zeppelin is more like the data processing part of it, a notebook for exploring your data, also for well, fast data visualization, and the machine learning part in my demo will be done by Spark. As we store everything in Elasticsearch, we have a visualization part of it, which is done by Kibana, Elasticsearch, Kibana, Logstash, and Beats. So we have all of the elk stack here, making that demo hopefully work. I'm sure that most of you know maybe some components, hopefully not all components, so I hope I can show you something new there. So I'll briefly explain why I chose all these tools and what the value of these are. We have the Beats framework, which is a rather easy to use and easy to configure component for simple data shipment. So getting data from a source system to, well, somewhere else. In our case, it's Kafka, but it really connects well to any other component as well. It acts as an agent on servers. The downside might be that it doesn't really scale well and it has no fault tolerance. So if your Beats agent goes down, you don't have any data shipment any longer from the source. And alternatives might be Apache NiFi or Apache MiniFi. MiniFi is a sub-project of Apache NiFi. So these would be other open source components in general capable of doing so. You have shippers for all data basically. So we are using a simple file beat agent here, but there's a metric beat agent for, well, collecting metrics, packet beat for network data, winlog beat for Windows event logs, audit beat for audit data, and so on. So you really have a lot of stuff going on in the Beats framework that you can use to get data from the source into your platform. Once it's in your platform, data integration, Kafka is kind of the go-to tool in the Apache Software Foundation world, at least. It's a publish-subscribe streaming platform itself, and it seamlessly integrates with a lot of other open source components like Beats in this example, but also Logstash or Spark. Kafka provides low latency and also high scalability in terms of high throughput, so it doesn't really matter whether you have 100 events per second or 100,000 events per second. Kafka is in general capable of dealing with that amount of data. One other good thing is it's independent of the data structure, the message structure, so it doesn't really matter whether you have JSON or CSV or any other kind of data. Kafka takes just everything in, and any other component can read it from your Kafka topics. Logstash, also in the data integration layer in here, is also rather easy to configure and connects well to not only Elastic related technologies, but also very many other technologies, like in our example, it would also be capable of pushing data to HDFS or pushing Slack messages or, well, whatever you can imagine, basically. It's also not very scalable and not really fault tolerant. So again, we would have the alternative of Apache NiFi here, which would be suitable of, well, dealing as a data integration component. We have a variety of inputs and also outputs, and from input to output you can also apply filters in your data integration layer. So that's what makes Logstash a really good tool to use in general. When we want to store data and we don't want to use like HDFS as an archive, we want fast access to the data. Elasticsearch is kind of one of the few tools which is capable of doing so because it's blazingly fast. It's a NoSQL storage system, and it has a very rich query DSL to kind of, well, let you retrieve the data that you want in a very easy way. It's scalable to tremendous amounts of data. So again, if you have a small use case, Elasticsearch can be used, but also if you have terabytes or petabytes of data, Elasticsearch is also capable of handling that amount. Well, Captain Obvious says it seamlessly connects to other Elastic-related products. That's right. So if we have Logstash, we can write to Elasticsearch, Beats can write to Elasticsearch, and Kibana can read from Elasticsearch. So that's why all of these components fit rather well together. We can manage our clusters, our Elasticsearch clusters, and monitor them by using Kibana. So we already have, by just installing another software component, well, monitoring and management of our cluster in more or less one piece. So that's rather nice and easy to set up. We have a lot of client libraries where you can integrate your, well, applications with Elasticsearch. So if you don't want to use Kibana for a visualization layer and want to implement something yourself, that is no problem at all. It has a rich RESTful API, which also offers easy integration if you don't want to use one of the client libraries that I just mentioned. Why should we use Spark for data processing? Or the question might be, well, why shouldn't we use Spark for data processing? Spark is really rich and enterprise-grade tool nowadays. So you can use it for any general data processing task that you have. And it has also the capability of a structured streaming, well, approach here, which we are leveraging in our demo. It is, of course, faster than traditional MapReduce options because of, well, how Spark internally works with formally resilient distributed data, and nowadays rather the data frames that everyone is using, and it has Scala, Python, Java, and R support. Zeppelin might be a tool that not all of you are aware of. So Zeppelin is, I think, still incubating in the Apache Software Foundation. It's a collaborative data science platform with also visualization capabilities. And it is excellent for playing around with and analyzing your data. So if you know Jupyter notebooks, Apache Zeppelin is kind of, well, the same, but it has full Spark support without the necessity of integrating anything. And you can also use it with, well, Python. You can access you can execute any shell commands. So Zeppelin is a rather nice tool which might have a lot more capabilities than Jupyter has out of the box. But it's like it's incubating at the moment. It might be not the most stable solution in the market, so Jupyter might be more stable, although it has not the best Spark support, at least out of the box. Why should we use Kibana for data visualization? Well, the reason is if we use Elasticsearch, we also use Kibana because that's just plug and play. We have a lot of visualization options for data, any data stored in Elasticsearch. We have a lot of drill down options, so this is just an example of a dashboard, and if you just click on any part of that, everything just automatically drills down to the applied filter by you as the user. It leverages everything which is within Elasticsearch, so as Elasticsearch can query tremendous amounts of data, you can query tremendous amounts of data by using Kibana on top of it in a very fast and intuitive way. We also can administer our Elasticsearch cluster by using Kibana, so we don't need any additional tools here. So how does the demo look like? We have a lot of movie reviews in that case from Amazon itself. I kind of borrowed them from a paper which I read. The paper reference is in the last slide, so everyone who's interested or might also want to use that data can reach out to the authors and they are happy to help you further. The data structure looks like what we see here. So we have in one review, of course, a review text, and that's where we do our machine learning on. We have an overall rating, so that's the rating the user gives. We have a reviewer ID, a review time, a summary, which is a summary of the review text, but also written by the user itself, and we have a Unix review time. The machine learning part is a rather simplistic approach here because it's not really about how well I can do machine learning, but rather how well we can do machine learning in a streaming context. So I just trained a very small model with 1,000 pure good reviews, so 5-star reviews, and 1,000 pure bad reviews, 1-star reviews. And the computation works like this. So we have an input, which is the review text. And when working with text, we need to split it up into smaller parts, words in general. That process is called tokenization. And the tokenization, or the output of the tokenization, is then what we compute the model on. And we are doing something which is called a TF-IDF model. TF stands for term frequency, so how often does a term occur in the review text. And IDF stands for inverse document frequency, and inverse document frequency means how rare is my term in my document collection, and document collection is the 1,000 pure good and or pure bad reviews in our case. The workflow now is just what we've seen here. So we have, in that case, a simple script which pretends that reviews are written on the fly, and the script just copies the reviews from one file to another file and reads then this file from my local file system and pushes it to Kafka to a topic named reviews. We have a Spark streaming context subscribing to this topic, and this Spark streaming context reads every review and does the same what we've seen here. So it takes the input, which is the review text, it does tokenization, and then it compares kind of the vectors from the review text to what we have computed in our machine learning model to say whether this is a good or a bad review. After the computation is done, the review with the computed result is again written to another Kafka topic, which is consumed by Logstash. And Logstash just takes it and pushes it to Elasticsearch, where we have our storage system, and then we use Kibana to visualize everything. So hopefully I'm able to show you everything that I have now told you, and that we have that red bar on top of that hopefully is not too bad, but we'll see how well that goes. Okay, so something is moving. I think everything should go well now. Data is now streaming in more or less real time into our system, and we just pretend to be a rather large online shop because we see the reviews flowing in every couple of seconds. Every couple of seconds means in that time we have an auto refresh here of 5 seconds. So every 5 seconds my dashboard is refreshed and takes all the newly indexed data into account. So I started that before we started this talk here, and now we have 600 and a couple of reviews indexed. And we see here the average of ratings is the average of ratings that the users gave. We see here 50% of, well, 50% or more of the data has 5-star ratings. And here we see our calculated predictions. As we only have 1 or 5 stars in our predictions, but our data has 1, 2, 3, 4 or 5 stars, we kind of can explain that our predictions are, well, not as good as the average of ratings in real, but we see it at least goes into the right direction. We can also see here the distribution of ratings the users gave and the distribution of predictions. And as we see, so this part here is the 5-star ratings as it is here, and we could at least pretend that looks rather similar. So we might say, okay, everything which is a 5-star rating in real seems to be a 5-star rating in well, our model computation as well, and everything with less than 5 stars might be the green part here, which is predicted as a bad rating. So this is just general statistics here, but we kind of want actionable insights from that. So let's see what else we have got. We have the top reviewers, which is, well, not that self-explanatory. So Amazon customer can be anyone. Amazon customer is basically anyone who doesn't give a name to his review. But then we have another guy, the movie guy, movies from A to Z, which is maybe even a real person reviewing movies, and that would be maybe one first actionable insight. So this guy here is interacting in our platform really well, and we might reward him or want to reward him with, let's say, a voucher, so he keeps interacting and giving reviews on our platform, on our review system, to keep him on our platform and also make the content that we provide more interesting to other ones. If we want to move down here, we see the top 20 reviewers that gave 4 stars or more to any product. And here we see kind of bad reviewers who gave 1 or 2 stars, well, certain amounts of time. So these all gave just 1 review, these gave 2 reviews, these gave 3 reviews. And that might be the next actionable insight that we get. So we might want to reward those who give good well, reviews on our platform, give them a voucher, and maybe we want to give them a voucher to not give any reviews more on our platform, because we don't really want bad reviews on our platform. So that would be another insight that we gain. Now when we come to the predictions, so that's only the statistics of the real overviews they gave, we see that we have top reviewers which give bad ratings but have good predictions. So we might want to look at these because users make mistakes and they might write a good text but accidentally give a bad amount of stars to the products they wanted to rate. So we could dive into these and see whether these are, well, for real bad ratings, which all, well, by accident have a good prediction because our machine learning model isn't perfect. We'll see that in a moment. So that will be one other actionable insight that we have. On that case here, we have bad reviews and, bad predictions, but a good rating. So it's just the other way around here. And we might want to dive into these as well to see how well that can be. But if we have a look at these numbers down here, we might want to tune our machine learning model as well, because we have the count of rating prediction mismatches being 228. 228 out of 700 is rather significant. In that case, we have the count of positive ratings and prediction matches, so 320 were okay. And here we have negative rating and prediction matches. So altogether like 400 are okay and 230 are not okay. And still missing would be the count of rating prediction mismatches for the, oh no, these are all in general, and these are split up in the positive and the negative ones. So we have a model which is better than flipping a coin, which is not bad, as we have a binary classifying system here, but it could be better. So in that case, our model is not as well as it might be. But as we only had like 2,000 reviews as a training data set, acting better than flipping a coin is not that bad, at least for these demo purposes that we have here. So that's kind of what we can do with Kibana to just visualize data that we have indexed. And as we have seen, we have a couple of components here, and we might want to recap how well the requirements were met in general here. So one key requirement was performance, so high throughput, low latency. And we can achieve that, in fact, with Kafka, Spark, and Elasticsearch as our central components, because they can handle a large or huge amounts of events per second. We also, but we didn't really see that, have achieved manageability because, well, everything can be rather easily deployed. We have containers for everything if we want to deploy everything as containers. All of our components provide APIs, so we can monitor everything and compare them with the KPIs that we have defined. We also have high scalability and also high resiliency, because if any of our components goes down and we have everything running in cluster mode, nothing really happens because we have other replicas which can deal with everything that, well, went down right at that moment. Data replication also means we can run everything in well, across data centers as well. So we don't have these boundaries that we need to take consideration of, but well, with components like any of them, in fact, data replication across multi data centers, it can be a challenge, especially if they are localized in different regions or different areas. So that might be something you want to keep into well, keep in consideration here. Data replication works well with all the tools, but across data centers it might not work as well as you might expect. The data protection and multi-tenancy requirements are also met. So by Kafka especially, we have this topic-based architecture, which means that if we have more than one tenant, they all have, or they all might have, their own topics which they subscribe to, so no one can really, well, get data that they are not allowed to. We can also track data lineage and provenance if we use tools like NiFi, because they have built-in capabilities of doing so. When it comes to compatibility and expansion, we can easily implement new use cases or extend existing ones, because that's usually just a matter of scaling the components. So we can scale more or less everything in real time without downage of any system, at least when it comes to replication. So if we have more consumers of the data or more data flowing in. If we need to resize, for example, our Elasticsearch cluster, that might not be as easy, but also there are strategies to do so. So that requirement would also be met in that case. What use cases can we kind of achieve or do when we build a real-time streaming analytics platform? We have, of course, seen we have some e-commerce use cases. So reward top reviewers, reward bad reviewers, automatic filtering of reviews is something that we haven't tackled yet. So if we want to detect bad language, for example, we could do so and prevent reviews from being published on the fly. If we detect bad language, we can also do something like search result optimization. So we don't want actually persons to control all the reviews all the time, especially if we have a lot of products. And if we see, and by we I mean our streaming analytics platform, if we see that one or more products get negative reviews all of the time in a short amount of time, we want to prevent them from being top results, because we don't want badly reviewed products being sold, because the chance that they are being sent back to us is rather high. On the other hand, we want those who are reviewed very good or really well on the top of our search result page. So that's another use case in e-commerce as well. Non-e-commerce, I think, yeah, some of the talks already covered them. So we have fraud detection, we have classification of transactions, which could also mean fraud detection in that case. We can recognize and also extract entities out of written text. So the first two might be a rather structured data use case. The third one here would be an unstructured data use case. We can do stuff like social media monitoring, which would be maybe semi-structured if we look at Twitter, which only has a small amount of written data. But it can also be like Facebook social media monitoring, where we might have more written data. With sensor data, we can have a look at anomalies, which is, again, well, rather similar to fraud detection up here. Yeah, that would be an IoT use case at the bottom here. Possible future improvements. So we've all seen that the model is not really perfect. As we're dealing with text, we can include or apply some natural language processing here, and one rather simple one would be we could exclude stop words from the reviews. Stop words are words which are not really meaningful, and not meaningful words don't really make sense in our machine learning model, so we could exclude them. But we need to be careful in terms of review. If someone says this was very funny or this was not funny, and then we apply a stop word filter, very and not might be thrown away, and then everything is funny. So that wouldn't be very funny in terms of our machine learning model, so we need to be very careful here and only throw out those stop words which are really not meaningful. We can also use word embeddings like word2vec, which is also a possibility that we can apply in our Spark machine learning context. And that means we go away from this rather simplistic TF-IDF approach, where we just count how often occurs a term in a certain review and measure how rare that term is. By word embeddings, we have more context and more meaning in it. So that would definitely be an improvement. We could have a look at how well the whole review is working against if we just use the summary, or if we combine both. Or we could also apply quality measurements, like the high frequency reviewers are the ones which provide, well, high quality reviews instead of those who only apply or give us one review. They might not be of that high quality that we can see eventually in what the high frequency reviewers give us. Also, the review length might be something we apply as a quality measurement, because that might also mean that the more length we have in a review, the more content we have, and that also would improve our machine learning model when we want to score reviews against that. So that's about it from the content side. This is the reference table. These are the papers that I mentioned where I got the Amazon reviews from. So feel free to read them or reach out to Julian McAuley, who is the one who gave me the data set that I worked with. And with that, I want to thank you everyone for your attention, and I'm happy to take questions now.